Class midpoints. We often find ourselves in a situation where we need to be aware of the data values themselves, but we may not have access to the list. So we have the frequency distribution, or in this case we simply have the limits. And from the frequency distribution in the previous video, we saw that there were 10 data values between 83 and 120. But without the access to the data set, we don't know what those 10 specific values are. There are many times where we need to sort of work with individual values, but we don't always have access to them. And that's where the class midpoint comes in. There are calculations and there are types of graphs that require us to use a single value, not a range of values. So the midpoint serves as a single representative value for the entire class. It's exactly halfway through the class. It splits it perfectly down the middle. The calculation for it is actually quite simple. It is simply an average or a mean of the lower and upper limits. For those of you who are familiar, I know we have not discussed the mean yet in this course, but it is simply the lower limit plus the upper limit, and then we divide by 2. That's how the average works. We add everything up and we divide by however many things there were. In this case, it will always be by 2 because each class has only one upper and one lower limit. We add them and divide by 2. So in this case, for the first class, we have 83 plus 120 over 2. That is 203 over 2. And again, calculators are our friends here. We divide that and we get 101.5. Of course, 101.5 would never be one of our actual data values, since all of our data was measured in whole numbers. But much like the class boundaries, if we acknowledge that the times are technically continuous but measured discretely, 101.5 can sort of make sense. Now, believe it or not, we only have to do that calculation for the first class. And that's it, the first class only. After that, there's a much simpler way to find all of the midpoints. Remember, the class width, in this case, was 38. 38 was the difference between lower limits of successive classes. It also is the difference between upper limits of successive classes. Actually, it's the difference between corresponding data values in successive classes, whether it's the very first, or the very last, or the second. If we took the second value from each class, 84 and 122, they would also be 38 apart from each other. So the midpoints are also 38 apart from each other. So this formula is great, but we only need to use it that one time at the very beginning. After that, since we already know the class width, we can simply add the class width over and over again. So the next midpoint should be 139.5. Let's just check to verify that. It couldn't be that simple, could it? Yeah, sometimes it is. Let's just check to try that out. 121 plus 158 over 2. Can it really come out to be 139.5? Well, 121 plus 158 is 279. Pull out the trusty calculator, and sure enough, 279 divided by 2 is 139.5. But I would say this is probably a lot easier to manage than this. Certainly, considering we have 6 classes to do it for, I would rather just add 38 each time. So, much like the way we constructed the limits, the class limits, we went downward, we will do the same thing here. We will simply add 38 going downward, and that will give us each successive class midpoint. And again, feel free to, of course, use a calculator. You can verify any of those by doing the original midpoint formula that we started with, but you would find that every one of them is correct. Much faster way to get the class midpoints when we need them. Again, like the class boundaries, the class midpoints are based off of the understanding that the data may be measured discretely but could technically be continuous. But even then, the midpoints do serve other purposes beyond that. As I said, the midpoint serves as a representative value of the class. It's not too high, it's not too low, it's right smack dab in the middle. So, again, from the frequency distribution, we know that there are 10 data values between 83 and 120, but we don't know what the 10 of them are unless we look at the actual data set. So, when need be, for certain graphs and for certain calculations, we can use 101.5 as a representative value of all of the data that's in that class.